In this lecture, we will discuss line search, which is essentially a single variable optimization issue that is applicable, that is useful in multivariate optimization. Okay. So till now we have seen single variable optimization, univariate optimization only in one context, in which the problem itself has just one variable. It's a genuine single variable problem, complete in itself. The solution of it is supposed to be the final output ready for use. And so we talked about a high accuracy for getting the final solution. Okay. However, for single variable problem, there is another context. It may come not directly from an application perspective, but from a multivariate problem. The original problem is multivariate with several variables, and the algorithm uses to solve that big problem uses a line search strategy. So in every iteration, after deciding on a direction, the algorithm requires a line search. In that, along a decent direction, one has to get the minimum of the function. And when the direction is chosen, then the problem becomes basically of a single variable. And that is a single variable problem. And that is how single variable problems appear in line search. Okay. So how far to move in this direction? That is the question the univariate problem tries to answer. Now, in the framework of the main algorithm, this little problem is often called the line search subproblem. Okay, so this is the other context of the single variable optimization problems. So after k iterations are over, we are sitting at xk, which is a vector of the kth iterate point. At this point, the main algorithm has generated a direction dk, hopefully a decent direction must be, okay, along which the present step is to be taken. Okay, so for this step, x will be xk plus alpha times dk, and we want to determine alpha. This scalar alpha denoting the step size in some sense. Why in some sense I say? Because this vector dk, though called a direction, doesn't need to be of unit magnitude. Because I need to clarify this, because it is typically understood that when we talk of direction vectors, we talk of unit magnitude vectors. That is not necessary. Okay, but you can keep it so. So the problem of the line search is to determine alpha. Okay, so this psi alpha is this. Here it is a single variable because xk and dk are known for this subproblem. So it is essentially a function of a single variable. And any of the methods that we studied earlier, quadratic estimation method, bisection method, everything, any of them can be used to minimize this and get the alpha star. So since we have got this direction dk from the main algorithm, we expect that it is a descent direction. That is, fx decreases along this direction, at least in the immediate neighborhood of xk. Okay, and this is something which you have to keep in mind, that descent direction doesn't mean that all the way it goes on decreasing. Right at this point it decreases. Okay, so right at this point, how do we make it concrete? we can say for infinitesimal delta, for a very small delta, psi delta is less than psi 0. Psi 0 is f of xk. Psi delta is, after it has gone, a little delta step ahead along direction dk. So as it goes ahead by a slight distance along that direction, the function value decreases. That's it. If you want to verify that a direction is descent direction, then rather than infinitesimal delta, which you cannot supply, you supply a small value. Okay, 10 to the power minus 4, 10 to the power minus 3, sometimes even 0.01 will do. Okay. Now, for differentiable functions, a more straightforward way can be found. You can divide the difference by delta and then take limit for differentiable functions. Okay. So for that, you can simply say that the first derivative at that point is 0. Okay. That is basically this. That means the gradient of the function at that point has a negative component along this direction. Okay. So that's the sense of a descent direction. But this you can talk about only for differentiable functions. This is general. So, of course, that infinitesimal issue connects the two ways of characterizing it. But for not differentiable anyway, the numerical verification you will do with a very small numerical value, finite. Okay. So this means that for line search algorithms, one bound is obvious. Alpha is non-negative, actually positive. Okay, because there is no point in sitting just here. On the upper side also, alpha may have a bound. In some algorithms, the algorithms means here the main algorithm of multivariate. In some multivariate methods, an upper bound is also supplied. For example, the Newton's method version for multivariate optimization, if line search is taken along with it, then the line search upper bound is 1. So the algorithm may supply an upper bound or may not. If it does not supply, then you have to do the bracketing. Okay. So let us take an example. We take a function of two variables, origin as the initial guess. So rather than xk, we are just taking x0. Okay. I mean, it's equivalent. So origin, so we start from origin where the function value happens to be 101 and a descent direction 2, 3. Okay. So 2 along x1, 3 along x2. So this is the direction. You see, it doesn't have unit magnitude slasher. And this direction apparently has been worked out by the main algorithm as a descent direction. You may verify also. Okay. So I verified the descent property of the direction. So for that, what I did, psi at a very small value, 10 to the power minus 3. Evaluated, that means f of 10 to the power minus 3 into 2, 3. So that is 0.002, 0.003. At this point, I evaluated the function, found 100.954, which is a little less than this. So it is a decent direction, no problem there. So since the upper bound for line search has not been given, lower bound is 0, we know. Okay, upper bound has not been given, so we do bracketing. And as we do bracketing, if a better lower bound also comes, we will take that. So we already have the value at 0, 101. At 1, that is f of 2, 3, we evaluate the function, get 68. F of 4, 6, that is psi at 2, it is 61 less. So further we go. At 3, we evaluate, we find 80. So we got the bracket. Psi 1, psi 2, psi 3. Going downward, then upward. Okay. So bracket we have got. and then we use one of the methods. In this case, I have used golden section search. Something else also will do. Okay. So in iteration 0, that is before iterations start for golden section search, for alpha equal to 1, 2, 1 and 3, we have the values. These are the x values. Okay. These are the psi alpha values which we are minimizing. And in the golden section framework, this is the left out point, this is the right out point. And at golden section points, we will work out two interior points, left in and right in. Okay. And at present, the border is 1, 3. Bracket is 1, 3. So at 0.618 and 0.31382 fractions from one end, we evaluate 2 points. This is at the 0.382. This is at the 0.618. Okay, so this is golden section ratio minus, 2 minus golden section ratio. This is golden section ratio minus 1. Or you can say this is 1 by phi into the current bracket size away from 1. This is 1 by phi square away from that. Okay. And at these 2 points, we evaluate the x point and fx, which is psi alpha. And this turns out to be the best till now, because till now the values that we have are 68, 80, 61 kind of thing. And this is also higher. So this is the current best point. In any case, to begin with, this gets positioned as left in at x1 position in the terminology of golden section search. This gets positioned as at the x2 position, right in. Okay, so left and right inside. And then, since this is the best till now, so the other one will become the boundary of the next bracket. And this boundary, 3, upper bound of the current bracket, will go off. Okay, so this right in immediately becomes right out. And according to the golden section operation, the other interior point shifts its place on the other side. From left in, it becomes right in. Okay. And then the upper limit of the bracket comes from here, because that point has now become the B. Okay. XU. Okay. And then over next iterations, as it happens that this point is so good that it never goes to the boundary. It stays for the next 6 iterations. It stays in the interior, keeps on shifting from right in to left in, then right in, then left in, then right in, and so on. In between, I expect you to verify these calculations later at your leisure. So 6 iterations, squeeze the bracket, and finally, after 7th iteration, we have the bracket here. Okay, 1.72 to 1.79. I have stopped here because after decimal point, 1 digit has started repeating. Okay. So an exit at this point gives us the best value of alpha till now in this line search round as 1.7639. Okay. Because right now the bracket is this, and we have 1 point in the interior already at a golden section location, which is this. Another point is yet to be found out if we go for another iteration. Okay. And the uncertainty is this minus one of these mod. Okay. So that much is the uncertainty, because true minimum can be anywhere between these two values. Okay. So this is what we have got. And how many iterations we made? We made 7 iterations, which means 8 evaluations after bracketing. So with the bracket, it was not 2 3, it should be 1 3. Okay, so there is a correction here. With the bracket 1 3, in 7 iterations with 8 function evaluations, we have got the best so far, which is this. We call it alpha 0. Okay, not alpha star. Why? Because we will take this alpha and put it in the context of the main algorithm. Okay, with an uncertainty of this, giving the next point x1 as this. This x1 is actually x naught plus alpha naught d naught. So that alpha naught we have produced just now. So this is the point where x1 we have found. Okay, and the uncertainty is this. Uncertainty works out to this. That is basically 0.04 times root over 13, because the direction vector was 2 3 having a magnitude of root over 13. So this times root over 13 happens to be this. Okay. So is it good? There are two possibilities of criticisms of opposing nature. One is that at the second place of decimal, there is a possibility of uncertainty in alpha, and that is quite high. Okay. And for the solution space, which is X space, there is a possibility of uncertainty in the first decimal place itself. So can it be called good? So a criticism can be made on accuracy, so far as single variable optimization problem has been concerned. Okay. Regarding efficiency, another criticism can be made from the other side. Out of 8 function evaluations, 6 are actually waste. Why? Because till the 7th iteration, we have got nothing better than what we had already got in the first iteration. Just look at this table once. At the end of the deal, we have got this point as the best so far. And we came to this point in the first iteration itself. Okay. So we could have said that, oh, this is good enough for us. Okay. Then the 6 next function evaluations we would have saved. And because the main problem is the one that is really to be solved. Okay. So we would be in a no worse position. Okay. Now, for these 6 iterations, what have we done really? We have basically increased our confidence level that this is indeed very good. Okay. Because at this stage, we knew the bracket to be this, which meant that at the end of first iteration, we knew that between 1 and 2.2361, anywhere the best point can lie. After 6 more iterations, we know that the best point actually will lie within a much narrower band of alpha values. That's all we know. But so far as our solution is concerned, it would be as good as it is now if we had stopped here. So this is another point. Okay. So after first iteration itself, why did we not say enough? Okay. Then we would be right here. In between 6 iterations, we would not have to make. Okay. So this is actually a valid point, and we have to address it. So, but the accuracy question we can answer very easily, because this is only a line search, not the final solution. It's a subproblem in an iteration. And for that matter, this value currently that we have may be quite accurate actually. Who knows? Okay. About this, we can think of different policies of line search. That is, after the first iteration itself, if we had some way of figuring out that this is actually a very good value that we have got somehow suddenly, and after this, several iterations are unlikely to produce much better. If we could develop some impression of that kind, then we would have confidence to abandon the line search along this direction and produce this itself as the result. So how to do that? In the current scenario, we did not know at the first iteration, after the first iteration, that several iterations after this would produce nothing better. We did not know that. We came to know that only afterwards. How to know that beforehand? That's a non-trivial issue, which we'll have to uh, come across properly and address. So from that, we get two different policies of line search. What we have been doing till now is called exact line search or accurate line search. In this, the true minimum along the direction is attempted up to a tolerance. If it is line search, considering its nature that it is an intermediate issue, you can keep the tolerance coarse. Rather than keeping 10 to the power minus 4, you can keep 10 to the power minus 1, 2. Okay. Or something like that. That you can do. Something of that sort we have done also. Okay. But procedurally, it takes the approach of finding the minimum. And in the context of line search problem, what it means, look at this. This is the origin x0, 0, 0. This is the direction 2, 3. The alpha. As alpha increases, you move along this point. And the bracket that we have got is 1 to 3. That means 0.23 to 0.69. So through 0.3, a curve, a contour of the function would pass, which has at all points of which the function has value 68. Okay, because we evaluated here 68. Now, the way I have made that roughly circular arc, it need not be circular arc. Oh, this is better. So through this, a curve would pass at all points of which the function will have value 68. Okay, this is the contour. At alpha equal to 3, where the function value is 80, another curve would pass. So you see that this curve is 80 here, and it will be 80 somewhere here also. Okay, because here it was 101, so it must have decreased. So what is happening? Since we have bound it high, low, high, so along this direction, the function value decreases, 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 and then again starts increasing, increases, increases, increases. So typically, each contour has two crosses with this direction, with this line, one somewhere here, another somewhere here. Okay. So here the angle in this zone, the angle between the direction and the contour curve is not very small. But as you know, as it decreases, 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 and then will start increasing again, that means in between there will be some zone where it will not increase or decrease much. Okay, so there a contour curve, okay, where equal function value will appear, that will be tangential to this line. Okay, and that tangential point is the minimum. Okay, so geometrically increasing alpha means cutting contours inward. Inward means towards the minimum. Increasing beyond a point, you start cutting them outward and leaving out the minimum point, which may be somewhere here. Okay, we want that point in between where there is just a tangential contact, for which the first order condition is this, that is, this is 0. Gradient is orthogonal to the direction decay. See, this is gradient, this is direction. So this is orthogonality condition. So this condition actually marks the first order necessary condition for exact line search or accurate line search. Okay, so if we find the tangent, so algorithmically we try to get this as closely as possible. Geometrically, we basically get the point of tangency of this line to one of the contours. The Inner contours don't have any contact with the tangent line. Outer contours cut it at two places. That tangential contour touches at one point. Basically, both of these intersections merge, and beyond it, both of them become complex, and that is why it does not meet at all. Okay, so this is what exact line search proposes to do. Up to what tolerance it does, that's a different issue. Another policy can be in which we don't even say that we are really looking for the minimum. We simply say modestly that we are looking for a very good point along this, from where we will take another direction and start moving again. Okay. So with progress, this is called inexact line search or inaccurate line search. Where to begin with, we have accepted that we are not looking for the best. We are looking for a very good one. Okay. So with progress of the process of the line search, as the point of tangency is approached, the rate of decrease is bound to suffer. And that means next iterations would produce very little improvement. And that wastage of computational cost we want to save in inexact line search. So this is one thing. But then if you go out too early, that means a direction which was developed by the main algorithm after some computation does not get searched enough. So we have to search this direction enough. We have to have enough iterations that this direction gets utilized to a good extent, and yet stop utilizing it further when the further improvements, marginal improvements, become very small. Okay, so this balance, to find this balance between computational effort and improvement, we need some robust rules, and those rules form the subject matter of inexact line search. Okay, so we need some rules encoding the notions of enough utilization of a direction and then exhaustion of a direction, that not much more we will get further. So if we had such notions earlier for that other problem, then with the help of those notions, after the first iteration itself, we could have detected that after these several iterations would produce nothing much better. Okay. So those rules are what we will talk about next in inexact line search. Right now, to summarize what we have done in this particular little lesson is that, first of all, we have to understand the two different contexts of single variable optimization. So if the single variable optimization problem appears as a problem of its own with its own application, then we have to solve it up to the best standards of accuracy. On the other hand, if it is a part of a multivariate problem, it's a sub-problem in an iteration, then our motto should be to get hold of a very good point along this direction from where another direction can do perhaps better. In exact line search, no separate procedural action is taken for such relaxation. It's only a matter of playing with the tolerance value. In inexact line search, we look for procedural rules to ensure a judicious balance between enough improvement and economical computation load. Okay, so that inexact line search is what we will do in the next lecture. Thank you.